Hey everyone, I want to talk to you guys a little bit about factors affecting solubility and factors affecting rate of dissolution. So let's get started with our lesson today. You will have already have written this definition down, but let's just refresh our memory on what solubility is. Solubility is the amount of solute that can dissolve in a given volume of solvent at a given temperature. Usually, our solubility curves are based on 100 grams of water. We know that there are three different types of solutions that you can have. You can have an unsaturated solution, a saturated solution, and a supersaturated solution. How will you know what type of solution you have if I give you a beaker of clear, transparent liquid in front of you? If you add a little bit of solute to this beaker and your solute dissolves, then you know that you had an unsaturated solution, meaning that your solvent is capable of holding more solute at that particular temperature. A saturated solution is one in which when you add some extra solute, the solute will just sit at the bottom of the beaker, no more of it will dissolve. Okay, so you'll see a little bit of that. And then if you have a supersaturated solution, you will know if you add a little bit of your solute, then all of the excess, the extra that you forced it to hold by heating it up, will come out of solution. And hopefully you saw some of those cool demos in the previous module. Dissolution, or the rate at which something dissolves, just refers to how quickly it dissolves. So we're going to be talking about rate versus the amount, which is called solubility. So these are the different factors that affect solubility and rate of dissolving. There's surface area, stirring or agitation, there's pressure, and there's something referred to as polarity, and then, of course, temperature. So let's talk a little bit about agitation. Agitation is when you stir something, shake something, and what it does is it increases the contact between the solute and the solvent, causing the rate of dissolution to happen much more quickly. It doesn't mean that you are going to get more to dissolve, it just means that it will dissolve more quickly. Let's take a quick peek at this little video here.
So now we're going to see the effect of agitation or stirring on the rate of solution formation. So to start out, I'm going to add 100 milliliters of water to each of our beakers. And then we're going to place about 1 gram of salt in each at the same time. So I'm going to stir one and not stir the other.
So again, we can kind of see there that the beaker that was stirred with the solute, obviously those particles dissolve more quickly. Over time, the other one would probably dissolve, but obviously takes a little bit longer. So what you would need to do is copy out the parts in red, not only indicating what agitation does in terms of the rate, but you need to explain. And it's the explaining that is super important. So what agitation does is it speeds up the contact between the surface of the solute and the solvent, causing those two particles to collide and therefore dissolve quicker. So let's take a look at the effect of temperature. So temperature has different effects on solids and liquids compared to gases. Generally, with solids and liquids, as we increase temperature, we will increase the speed at which the particles dissolve, but also the amount. And we saw that with solubility curves, if we increase temperature, we often can get more of the solute to dissolve. So that's referring to solubility. But an increase in temperature also increases the rate. And that's because we can see with this little animated GIF here, what temperature does is it increases the kinetic energy that the particles have. So kinetic energy means movement. If the particles are moving faster, then that means the solute and the solvent are coming in contact more readily, more frequently, and therefore they will dissolve much more quickly. So temperature is a factor that affects the rate, but it also affects solubility, meaning the amount that can dissolve. So again, let's just recall, here's our solubility curve. With most substances, as you increase temperature, you will increase the amount at which something will dissolve. So if we take a look at, let's say, sodium nitrate at the top here. So at 20 degrees, we would go up and we would see that we could dissolve roughly 85 grams in 100 grams of water. If I increase the temperature to 70 degrees, I go up and I will have a saturated solution when it hits this line. So just under 120, so let's just say 118 grams of sodium nitrate will dissolve in 100 grams of water. You're going to notice that the decrease happens with temperature whenever you have a gas. So ammonia and sulfur dioxide, those are gases. So that has an opposite effect. Temperature causes there to be less that can be dissolved at higher temperatures for gases. Okay, so let's take a look at that on the next couple of slides. So when we talk about gases, if we heat gases up, just as we do solids and liquids, we've given them so much kinetic energy that they will now have the ability to escape the liquid. And so, what that does is it causes less of the gas to stay dissolved. Here's a cool demo. Let's take a look.
Hi everybody. In this demonstration, we're going to be looking at factors that can change the solubility of a gas in a liquid. The gas that we're using is carbon dioxide. The liquid is water. So we're using a bottle of seltzer water, which is bottled at very high pressure, pushing carbon dioxide molecules into solution in the water. So what we're going to be using are 3 different bottles of seltzer water. I've got one that's been sitting out at room temperature, another one which is in a warm water bath, so we're heating that seltzer water up. And then finally, the third one here has been sitting in a large beaker with ice water in it. So we've got seltzer water, which is really cold, seltzer water at room temperature, and seltzer water, which has been heated up to quite a warm temperature. So we're going to take a look at what happens when we open these bottles. So this is the seltzer water which has been left out at room temperature. So I'm going to go ahead and open this up and let's take a look, see what happens as I open the cap here. Okay, so we can see that it fizzed up quite a bit, and what's happening right now is the carbon dioxide molecules, which were dissolved in the water, are coming out of solution. So that's producing the fizz, the bubbles that we see. And I kind of made a mess here, so I need to clean up before we look at what happens to the bottle that was in the cold water versus the one that was in the hot water too. All right, next we're going to take a look at what happens when we open the seltzer water, which was placed into the ice water bath. And just so we can see this a little bit more clearly, I'll just wipe off some of the condensation that's on the bottle before I open it. We'll try to do that quickly, just to remove some of that condensation so you can see what happens here. Okay, so here we go. We're now opening the seltzer water bottle that was placed into the ice water bath. We can see that the carbon dioxide, which was dissolved in the water, is coming out of solution. I want to think about comparing how rapidly is the carbon dioxide coming out of the water when it's cold versus how quickly did it come out of the water when the water was at room temperature. Not as big of a mess to clean up this time. For the last part of this demonstration, let's take a look at what happens when we open the seltzer water that was placed into the hot water bath. I think I might get messy on this one. Let's see what happens. Okay, my custodial staff is not going to be happy with me, but hopefully after seeing this demonstration, you get a better feel for how the temperature of water can change the solubility of a gas in the water.
So you can see at the higher temperatures, what ends up happening is we've given a lot of kinetic energy to those gas particles and they come out of solution. So they are less soluble. So I always kind of think about this with relation to pop. When you have warm pop sitting out on the table, it often becomes flat, right? So it has less carbon dioxide dissolved in it. Another connection that we can make to the solubility of gases is in different bodies of water, like a lake or a pond. If the water gets too warm, then what ends up happening is there's less carbon dioxide and less oxygen that stays dissolved within the water. If there's not enough oxygen in the water because it's too warm, all of that gas has come out of solution, then therefore there's not enough oxygen for plants and for aquatic organisms to survive. So this is an image of sort of like a mass death of fish due to the lack of oxygen. It's not because of pollutants, but it's because the temperature of the water is too high. So, this is a big concern, especially with climate change. Just raising the temperature 1 degree can cause very adverse effects. When we are talking about surface area does not increase the amount that can dissolve, but it definitely does affect how quickly something dissolves. So, surface area affects the rate of dissolution. And I want you to think of surface area in terms of particle size. So, here we have a cube. Let's just say that that's 1 gram. And we have the same cube. And what I've done is I've chopped it up into smaller pieces. Think of this as windows of opportunity, points of contact between the solute and the solvent. Here we've got 6 sides that are exposed. So surface area is really a surface phenomenon. Here, if you were to take a look at all of these cubes, you would do 6 times the number of cubes that we have here. So 3, 6, 9, 12, 15, 18, 18 times 6, whatever that is. That's how many windows of contact you can have between the solute and the solvent. So this would be considered higher surface area. The greater the surface area, the smaller the particle size, but the quicker the rate of dissolution. So think about table salt will dissolve much more quickly than a chunk of salt. Okay, the table salt is finer particulates. Here, think about if you were to look at this, this is a clump of solute being surrounded by water particles, let's say, or hydrogen atoms, and it's trying to get to the interior, but it cannot. But when we have smaller solute particles broken up, we have greater contact and more accessibility. Let's take a look at this demo.
So now we're going to see the effect of surface area on the rate of dissolving. So I've got 2 different types of salt here. I've got your typical granulated salt, and then I've also got a big chunk of what's called rock salt. So this is just one big chunk of salt. So the chunk of salt weighs about 1.75 grams, so I've got 1.75 grams of granulated salt as well. So I'm going to add the same amount of water to each beaker. So here I'm adding 100 milliliters of water and 100 milliliters of water to the other beaker. And we're going to place both types of salt and see which one dissolves first. So I'm going to drop these in at the same time. There goes the granulated and the rock. So in a couple of minutes, we'll look and see which one of these has dissolved first. So some time has passed, and let's check to see which one has dissolved the salt. So if we look in the granulated salt, if I stir this, we don't see any of that granulated salt sitting around in the bottom. If we look at the rock salt, we can still see that there's this giant piece of salt floating around in the bottom here. Just going to go in there and grab it out. So we still have this huge chunk of salt that hasn't dissolved.
So we can see greater surface area, smaller particle size, rate of dissolution happens much more quickly. Hi, let's talk about pressure. Pressure only affects gases because gases can be compressed. So the effect of pressure on gases, the greater the pressure, the more gas will be dissolved. And again, think back to a bottle of pop. It's under pressure, and so we're forcing the carbon dioxide to stay dissolved in that liter of pop. When you release the pressure, right, gases come out of solution. So here's just an image. If you have gases, if you increase the pressure above, we are forcing the gas particles to go into solution. And this relates to nitrogen narcosis, also referred to as the bends. So, what ends up happening with the bends is you have this gas tank, if you are scuba diving, that is made up of mixture of gases that we have here on Earth to simulate what we would breathe. So, nitrogen, which is about 78% of our atmosphere, 21% oxygen, and so forth. So, what ends up happening is the scuba diver breathes this in, and that gas gets forced into our lungs and out through our circulatory system and circulates through our entire system. Now, as we descend, what ends up happening is there is greater pressure acting on our body. So, greater amount of gas from the scuba tank that's being breathed in gets dissolved into our blood. Now, what happens is if the scuba diver comes up too quickly, the pressure acting on that scuba diver lessens because as we go up in altitude, there's less pressure acting on us. And so, if this scuba diver comes up too quickly, the gases that he breathed in or she breathed in get forced into the circulatory system, will come out of solution. Just like unscrewing the bottle of pop, all that gas comes up and out. And then where does that go? Well, if that happens, this can be very deadly for the scuba diver because that nitrogen gas that comes out of the blood too quickly can be extremely painful, causes painful bubbles within the veins and arteries. And if that happens, and we can't get you to a special decompression chamber like this that can force the gas back into your body, you can have crippling pain and can even lead to death. Okay, so here, if you're ever scuba diving, you have to take the required courses, but you need to come up at different intervals, stop for a little while, and then you continue to come up. There is a really cool video that I'm going to link on the next slide here about pressure changes underwater. I'd really love for you to take the opportunity to watch that. Really cool information there. And the last factor affecting rate of dissolving or amount of solubility is called polarity or the type of solvent. And what the take home message here is that you have to understand that there are two different types of interactions that occur that we talked about at the beginning. There are attraction between molecules and attraction within the molecule. Between molecules is called intramolecular attraction. In order for solute particles to dissolve, you have to have an intramolecular attraction between the solute and the solvent in order for dissolving. So, just refreshing our memory from Unit 2, we have intramolecular bonding called covalent bonding and ionic bonding. Ionic bonding is the transfer of electrons from a metal to a nonmetal, creating cations and anions, and it's the difference in charge that holds them together. So, this would be a type of solute, like table salt. Table salt, sodium chloride, would be an example of an ionic bonded compound. Covalent bonding happens when you have two or more atoms generally between nonmetals, sharing their electrons to complete their octets. And in doing so, they can share those electrons equally or unequally, polar or nonpolar. So, covalent bonding and ionic bonding are types of intramolecular bonding. Okay? So when we have polar, remember there's an unequal sharing of electrons, and that's because one of the atoms is more electronegative. It likes to have the shared pair of electrons closer to it most of the time, giving a region of the molecule a partial negative or a partial positive charge. So, water molecules are polar molecules, but if another water molecule is attracted to another water molecule or to a solute particle, the attraction between is called an intermolecular bond. So, when we take a look at this example here, and it's a little bit hard to see here, if you have two liquid layers that do not mix, it's because the intermolecular attraction between the solute and the solvent, this in this case, it happens to be two liquids, these would be immiscible, meaning this liquid is not soluble in the other liquid. The intermolecular attraction between the two are not similar enough in order for them to dissolve. So you will get two layers. You will get a heterogeneous mixture. So here is what it would look like if you took cyclohexane, which is a type of solute, and you dissolve it in water. We see that the water is represented by this type of particle here, you can see here. The two do not mix because cyclohexane is a non-polar molecule and water is a polar molecule. In order to get two substances to dissolve, what has to happen is they have to have similar polarities. So we use the saying like dissolves like. Nonpolar will dissolve in nonpolar. Polar will dissolve in polar. Nonpolar will not dissolve in polar. Okay? We have to have like dissolves like. So again, let's take a look here. You have solute particles that are attracted to one another. You have solvent particles that are attracted to one another. If a solute is going to dissolve in a solvent, they have to have similar polarity. The intermolecular attraction between them has to be greater than the attraction between the solvent particles themselves and the solute particles. So that's the only way that you can get something to dissolve. So here we go. Nonpolar dissolves in nonpolar, polar dissolves in polar. And the last one you need to know is that ionic compounds will dissolve in polar solvents. So, ionic compounds, remember, are made up of cations and anions. They are charged particles. Polar compounds have partially charged ends. So, those partially charged ends can be attracted to the cations and the anions. So, we've got an attraction there. So, we will have dissolving happen. We do not have ionic solvents. We just have nonpolar solvents and polar solvents. But the type of solutes that you can have are nonpolar, polar, and ionic. So here's just a little summary table for you to see type of solute. Will it dissolve in polar solvent? Will it dissolve in a nonpolar solvent? Like dissolves like. Here's an application. When it comes to vitamins, different vitamins are either water soluble or fat soluble. So when we think about vitamin C is a water soluble vitamin. So that means that if you take too much vitamin C, your body will just actually pee out the excess, or you'll sweat it out. It will come out in the water portions of your body. Okay. Now, your fat in your body is a non-polar compound. Fats are non-polar. So vitamin A is also a non-polar compound. Non-polar, like dissolves like. If you take too much vitamin A, you can actually overdose on vitamin A because it will get dissolved in your fat and it stays within your fat. And what can happen is it can cause things like hair loss, blurred vision, liver damage. So, fat soluble vitamins should not be consumed in excess because you don't have the capability of getting rid of that as easily as water soluble vitamins, which you need to replenish more often. So, there is a good application for you. So hopefully that gives you a bit more information that you require to fill out factors affecting solubility and rate of dissolution. I'd like you to also take a look at the slides that come after this lesson to use in your aiding of completing that worksheet.